Okay, everyone, let's get started. I am Jason Bakos. I am giving a guest lecture today for Dr. Yan. I will be here just today. Dr. Wong, I believe, will be delivering your lecture on Thursday. Those of you that are computer engineering majors will be getting to know me really well during your senior year. And if you're a computer science or electrical engineering major, you may be taking one of my courses as an elective in your senior year. I teach digital design and embedded system design, advanced digital design and embedded system design. I used to teach this course. Yeah, 313 and 611, that's right. Okay, so the topic of the lecture today is memory hierarchy. By this point in the semester, you all should be fairly comfortable with the notion of a load store machine. You heard of that before? Know what that's all about? Anyone know what that is? So load store machine refers to a processor that can only perform arithmetic operations on values that it has previously loaded into its registers, and then so it has load instructions for loading in values from memory into registers, and then it has store instructions for storing values in the registers back out to memory. The registers are assumed to be internal to the CPU. So all the number crunching the CPU does is on values in the registers. It can only do calculations on values in the registers. And then it has to exchange values between the registers and the RAM in order to get any kind of data in or out of the CPU. So that's the way it uses load and store instructions essentially to communicate with the outside world, because everything else is just inside of its own, it's under the hood, essentially. Right, does that make sense? Now, have any of you ever thought about why they're set up like that? What's the reasoning behind a load store machine? Why can't you just perform calculations on data directly in memory, as opposed to having to worry about bringing it in to registers with load instructions and bringing it out with store instructions? Yes. Yes, it's a question of access time. The presumption is that registers are really fast to access. You can read a register or write a register in a clock cycle, whereas any loader store is accessing another external memory of some kind, and it's slower. But up until this point, you really haven't learned much about that. You know, what is the reasoning? What is the reason for that? So today we're going to talk about that. Why are registers fast? And why is other type of memory slow? As a matter of fact, there's all kinds of memory technology now. I think Dr. Yan probably mentioned, I think he mentioned that he's talked about SRAM and DRAM. These are basically two, essentially, circuits that store a bit. A DRAM is a circuit comprised of a capacitor and one transistor, and that's a DRAM, and an SRAM is basically two inverters that are pointed to one another and that are cross-connected. So there's 6 transistors to store 1 bit in SRAM. But basically they're both sort of equivalent in that they store a bit. Just two different ways of doing it. And then of course there's magnetic disks, which I don't think anyone uses anymore. And then you've got flash memory, which is becoming more prevalent, not only in for storage and phones and such, but also even in like in servers and as storage all over the place. There's also new types of memory technology coming out called memristors. That there's several companies trying to develop that technology. That's a non-volatile memory technology. But the point is, there's all kinds of memory technologies, but don't get caught up too much in that, because the point of this is, in general, the bigger the memory capacity, the slower it is in general. So the reason why registers are fast is not really because of how the registers are physically constructed. That's kind of irrelevant. The important thing, the important note there is that the register file is small. You guys know there's only 32 registers. It's not, the register file is really tiny. It's only big enough to store just a few values in, right? A small handful of values. The main memory of your computer, the RAM, is much, much bigger. The disk is much, much bigger, right? Flash memory is bigger. But in general, the bigger the memory, the slower it is. And that spans every type of memory technology. Yes?
If the actual design of the circuit that stores the bits in different types of memory is relatively similar, why is there such a big price difference in SRAM, DRAM?
That has to do with density. So DRAM is 6 transistors per bit. So you have to have a much bigger device to store the equivalent amount of data as a DRAM chip. But see, the problem is that the speed is determined by the decoding latency. So there's a decoder. You guys should have learned about decoders in 211. Decoders are really important for memory because the decoder, every memory has a decoder in it somewhere. It doesn't matter what kind of memory you have. And the decoder is what takes the address, the memory address, which is a binary number, and it converts it into a unary number. It basically converts it to one active wire out of a whole set of 2 to the n wires, where n is the address size, right? That's what a decoder does. The bigger the address is, means there's the higher capacity, because the larger address means more locations, means higher capacity, means bigger memory. The bigger that address is, the more outputs the decoder has, and thus the longer the critical path is through the decoder. So I don't know if you guys ever implemented a decoder with like regular logic gates in 211, but if you implemented a 2 to 4 decoder, it would go through like 2 logic levels. But if you went through an 8 to 256 encoder, so 8 bits to 2 to the 8th power, which is 256, that would be a much bigger circuit, and it would have a much longer critical path that the signals would have to traverse through it. So it's a bigger decoder, it's a slower decoder. So don't get too caught up in memory technology or even the price of memory technology. It's a fundamental law that the bigger the capacity of a memory, the slower it is, and that applies to everything. The one example he might have covered in the last lecture is if you think about like your desk. If you have a desk and you got a bunch of papers on it, those are the papers that you're sort of actively using, and it's very quick to get to them, but your desk has a small capacity. It's just the top of your desk. But you have a filing cabinet then that has a bigger capacity, but it takes longer to access documents from your filing cabinet, right? And then if you need even bigger capacity yet, you have some warehouse with boxes in it, and it takes a really long time to get there. So this is nothing even unique to computing technology. It's just a fundamental law of nature that the larger the capacity of a memory is, the slower it is, right? So that's the idea with memory hierarchy is we have programmers and users and everybody, they want to have the best of both worlds. They want to have a very large capacity memory so you can store all your data in there. But they don't want to pay the price for that, which is slowness, right? They want to have performance that is kind of like as if you were talking to, as if you had a small memory, but they want to have the capacity of a large memory, right? And so memory hierarchy is a way to try to satisfy everybody. And the idea is that you build this hierarchy where you've got the processor with its registers kind of at the top of the hierarchy. So that's the registers are the smallest memory and the fastest memory that's available. And then under there you have some progressively larger capacity memories that are also progressively slower. But each one of those levels of the memory hierarchy contains all the data of the level above it and more, right? So if you're at this level of the memory hierarchy, this memory contains everything, is a superset of the memory level above it. So this kind of backs up, this larger memory is a backing store for the smaller memory, right? And so when they have this picture, and this is a little confusing because they sort of focus on the technology, but see these days, this is kind of out of date because a modern day CPU that you buy off the shelf now You go to Best Buy, you buy an Intel processor. It's got, of course, registers. And Intel processors only have 4 registers that are visible to the programmer. 4 general purpose registers, A, B, C, and D. It's not like MIPS, you got 32. But you've got registers in every processor these days. And then they have a level 1, a level 2, a level 3, and a level 4 cache, all in the CPU. And they're all made with SRAM. The only difference is that each level is bigger than the previous level. That's the only difference. They're all SRAM, right? Now there's some other differences too, like sometimes there's more ports, more numbers of, higher numbers of simultaneous accesses you can make on higher levels of the memory hierarchy and so forth. But the main difference is, the size. And then nowadays, there's this new technology called high bandwidth memory, which is a 3-dimensional memory structure that they're putting on. GPUs already have it. The Intel Phi processor has it. The newer processor will have this high bandwidth memory, which is like a 5th level of the memory hierarchy that's even a little bit slower but bigger than the level 4 cache, right? And then of course you've got your DRAM, and then also people are now incorporating flash memory as part of the memory hierarchy. So not just like a solid state disk, but an actual memory that backs up the DRAM, right? And that's so there's all these different technologies coming in, but it's basically just size versus delay, right? So that's the hierarchy. Again, they talk about price, but I wouldn't see. This is a little bit misleading actually, because they imply that if we only had enough money, I could just buy a huge SRAM and just replace my DRAM, and the whole computer will be radically faster. But that's impossible, because even with an unlimited budget, as you scale up the size of the SRAM, there's no way to get around the fact that it's going to get slower. It's still going to get slower, even with an unlimited amount of money to spend. So don't worry too much about the price or the technology. It really has to do with the size. So let's see, I already covered that. So he's got a picture. This is sort of for context a little bit. I'm not sure how many of you these days have built your own computer or upgraded your computer, but normally, you have a motherboard, and then you've got these RAM modules that are on these little sticks that you can use to expand the memory, and these are DRAM, and these are typically thought of as the main core memory, but that's changing as technology evolves. That may not be the case for much longer. The CPU design, and this is wow, this is really downsampled here, but this is the CPU design that you covered in chapter 4, I believe. And this was a little bit confusing in my opinion, because the data memory and the instruction memory were shown as if they were part of the CPU design, right? They were sort of in this block diagram. And this is also kind of weird because the cache, and he has a picture of the cache, so this is the Intel chip. The cache is part of the die. It's on the die. It's on the CPU chip. So it is an SRAM that is incorporated in the same chip. And then once you go below the cache in the memory hierarchy, you go off chip, so you come out of the socket, this white socket. You come out of the CPU socket, you go onto the motherboard, which is real slow because the motherboard has a lot of capacitance in those big fat wires. And then you go off to these DRAM chips, right? So the idea is that when you look at this design, it sort of implies that the CPU is all just one monolithic thing. But you have to kind of think of these memory blocks here as sort of being external to the CPU, right? And that sort of corresponds to the notion of a load store architecture. The idea behind a load store is that you're doing loads and stores to exchange memory, to exchange data with registers, where the data is sort of external to the CPU somehow, even though you might just be accessing the cache, which is still technically on the same chip. It's just there's a penalty associated with a load or store. You guys make sense? So it's a little confusing the way they present it, right? So, but just the only thing you have to think of is that the memory hierarchy is just like a pyramid of increasingly bigger and slower memories. That's all you have to worry about. Okay, so how does the memory hierarchy work? I mean, so what is the goal here? The goal again is to make, from the perspective of the programmer is supposed to be presented with a memory that is both large and fast, which violates the laws of nature. So how do we do this? What's the trick? Well, the trick is this idea of locality. Locality is a characteristic of access pattern. So in order to understand locality, you have to understand what an access pattern is. So he's got this loop here, this for loop. And this for loop sets, it has a scalar value, a local variable called sum that's initialized as 0. And then you go through this for loop, and every time you go through this for loop, which is only one line of code, the body of the for loop is one line of code, you read a value out of this array called A, and then you just accumulate it into this sum. So you look at this, and you have to think of what the pattern, the access pattern is the dynamic sequence of memory addresses that are accessed from when your program is run. So the confusing part here is you look at this is a very simple loop, very small snippet of code, but when you run this, if I was the memory and the CPU is running this, I would see the CPU asking for, even though it's a small program, the CPU is going to be asking potentially for a huge amount of data based on this n value, which is the limit of this loop, right? So the access pattern is the sequence of memory addresses that the CPU is requesting from me as the memory while it's running. So what is the access pattern of this loop? Well, it's kind of hard to, the C programming language kind of abstracts that away. It's kind of hard to tell. You have to first of all know that in C, in the C language, and in most programming languages, if you have a single dimensional array, like this A array, all of the elements of that array are allocated in memory in consecutive words, right? So as I'm going through this for loop, because I'm indexing, so this array is A, the array of A starts at some memory address that has an offset, but then as I increase the index value, it's going to walk through the array, and it's going to walk through consecutive addresses. So it's basically reading one word after another, and the words are in one block, one contiguous, non-interrupted block of addresses. And because if we assume that A is an array of integers that are 32 bits each, then the addresses are going to walk by 4. So it's going to be, it's going to start out as whatever the index 0 is, wherever A starts, and then it's going to add 4. The next address is going to add 4 plus that. So if A starts at 0, it's going to be 0, 4, 8, 12, 16, 20, 24, and that'll be the access pattern. Does it make sense? So the access, so this is the access pattern is it's an ordered list of addresses that are issued by a program to the memory. Locality is a property of an access pattern. And what is the property? Well, there's two types of locality. There's spatial locality and there's temporal locality. Temporal locality says once you access an address, you're probably going to access a nearby address in the future. Well, that's actually happening here, right? Because this loop is saying, give me 0, 4, 8, 12, 16, 20. And so there's locality there. There's spatial locality because the access pattern is sort of restricted to this array of A, right? And by the way, while it's going through here, nothing really else is going on. It's just this thread is going to be issuing that access pattern. It's just going to be reading A for the time that it's in that loop. Does that make sense? Now, there's another type of locality called temporal locality that says once you access one word from memory, you're probably going to access it again in the near future. Do we have that here? No. Actually, this loop, as it's shown, has no temporal locality because we only read each element of the A array once, right? Now, we might be accessing it out somewhere else, but yes?
What about accessing like I in and sum over and over again?
I is, so when this is compiled, I is probably going to be in a register the whole time. You're probably not going to be reading I out of memory, or reading it, using it to index A, updating it by 1 and then storing it back and then reading it back. It would be kind of redundant because the whole purpose of registers are to hold values like I, because it's something that's accessed very frequently, and it's not something that's ever really used after this loop, or it might be kind of recycled, but it's not going to be necessarily accessed. So the compiler hopefully won't even bother loading or storing I during this loop. It'll just be in a register. Same thing with sum, right? I mean, sum will be, probably after the loop is done, it'll store sum back, but it's not necessarily going to keep writing sum. But if it did, then you'd be right. That would be an example of temporal locality then. If it did, I'm speaking sort of from a practical way, but you're right. If it was loading, if it kept accessing sum through this, or I, then that would be an example of temporal locality, right? Because it would be a same value that it's reading over and over again, or not reading or writing, right? So another example would be, let's say that this was an FIR filter, a finite impulse response filter. That would look very similar to this, except this one would access A at I, but also A at I plus 1 and A at I plus 2. Right? So it would access 3 elements of A per iteration, and then when you go to the next iteration, it'll increment I, but 2 of those 3 things that it accesses in the next iteration will have already been read in the previous iteration, right? Does that make sense? Because you've got kind of like a sliding window, sort of. So that would be another example of temporal locality. So yes?
Why doesn't that go for sum, because you're adding sum plus A at I?
It possibly, so the question is whether or not it actually stores and loads sum, right? If it's storing and loading sum, so first of all, one of the issues here is that this is an example in C. We don't know how this C language snippet was translated into assembly code. In order to figure out which of these variables and arrays are being accessed into the memory, we need to know which variables are being loaded and stored during this loop. And we don't know that because the high-level language abstracts that away from us. I made an assumption that probably I and sum are not being loaded and stored, at least not during this loop. Right? I assume that only the A array was, because why? Because the A array is too big to be stored in the registers. It's a big array, whereas I and sum are just scalar values. They're just one value. It would only take one register to keep sum and I inside a register. It would take 2 registers, one for each of sum and I. But that being said, that's an assumption I'm making. It could also be the case that the compiler, when the compiler translates this to assembly language, it might be also issuing loads and store instructions for sum and I as well. It could be. I just think that would kill your performance if you did that. But then again, maybe if you compiled this with the lowest optimization setting on your compiler, it would do that. So yeah, that's a good point. You guys are both right. I mean, you're accessing sum and I over and over again as the loop progresses, and that is an example of temporal locality. Yes?
If we were if you had a different method, we were calculating a bunch of different areas for circles, and we had pi as a constant somewhere, would pi be the temporal locality variable?
Yeah, if you kept loading it. Yeah, the question is, the locality comes from, the access pattern comes from loads and stores. So just keep that in mind. It's the registers, we don't include the register accesses as part of the access pattern. That is a good point, though, that it's up to the code. Different codes, different loops will have different access patterns. It just depends on the loop. In general, if you have a loop like this that is very simple and is structured, a loop like this is what you find in linear algebra code, image processing code, signal processing code, graphics code, stuff like that. Very simple, predictable access pattern that sort of just scans through a block of memory, or possibly through a 2 or 3 dimensional block of memory, but it goes in a predictable way. If you have a graph application, like if I have a program that figures out how many Facebook friends away I am from Kevin Bacon or something, that would have that wouldn't have as much locality because it would have to access data from all over the place, right, in sort of an unpredictable way, right, because it would have to follow it would have to follow links. It would have to follow connections between one person to the next. And so you wouldn't necessarily be accessing a small block of data. So that would be an example of something that has very little locality. But the locality is purely a function of the code and how the code behaves when you run it, right? Make sense? So this has, this has spatial, a lot of spatial locality. So the idea then is, if you have locality, then you take, basically you take the working set of the program, the data that it's accessing now and that it is likely to access in the near future, and you put that in the fast memory that's small, right? And so as long as you, basically the idea is with temporal locality, the first time you access something, you have to pay this penalty because you have to move the data from the larger, slower memory up into this faster memory, the cache. Think of that as the cache, right? But then if you have temporal locality where you're accessing that data a whole bunch of more times in the near future, then it's available in the small memory, and the processor sees that as having a fast access time, right? Does that make sense? So if I have a variable, I will pay an initial penalty. They call that a compulsory miss. The first time I access something, I have to bring it out of the big memory. I put it in my small memory. But then every time after that I access it, if I access it a whole bunch of times, then I get the fast access time of the small memory, right? Likewise, with spatial locality says I accessed something, I'm probably going to access something around that part soon. So I am going to prefetch all of the surrounding memory locations. So if you ask me for address 10, I'm thinking, well, he wants address 10, probably he's going to want 11 and 12 and 13 and 14 soon. So I'll just go ahead and, since I'm already kind of committed now, I've kind of committed myself, I got to go to that slow memory and grab stuff. I might as well grab a whole block of data surrounding the address that the user wants, the program wants, because I'm going to bank on the fact that in the near future he's going to want that other words around that location. And that's how you exploit spatial locality, right? So the idea behind temporal locality is, once you access something the first time, you're probably going to access it again, so bring it on up. And then spatial locality is the idea of, essentially, whenever you access something for the first time, go ahead and just grab the surrounding elements there too, the surrounding words, and bring those in as well. So bring a whole block of data in surrounding that one that was accessed. Yes?
How does the computer know if you are using spatial or temporal?
It doesn't. It all has to do with the performance of the cache. So actually that's an excellent question. That will lead me into this. So there's two terms that you have to be familiar with, a hit and a miss. A hit is when the processor accesses a memory location with a load or a store, and the address that it's looking for. Now keep in mind, this is based on addresses, right? Not the contents of the address, but the address. So if it requests an address, and that address is in the cache, so think of the cache as a set of addresses that are stored in the cache. They don't have to be consecutive addresses, just a set of addresses, just a bag of addresses. If I access an address and it's in the cache, that's a hit, and I'll get a fast access time out of that. But if I access one that's not in the cache and it has to be retrieved, not necessarily from main memory, but from some lower level of the memory hierarchy, that's a miss, and I will pay a higher penalty, a higher access time. The problem is there's no way to predict this ahead of time, right? So when you run an arbitrary program on an arbitrary CPU, it will exhibit some cache performance that is a function of the code itself and how the code is accessing the data, but also the cache technology that's being used, right? Because I might have one computer with a better cache than another, right? Normally, that's one of the biggest differentiators between an embedded computer that's in your cell phone and your desktop or server computer is the cache. The cache in these processors suck. It's really bad. It doesn't have a lot of the features that a laptop cache will have, just because the more features you put in your cache, the more energy, the more power it consumes. So if you want something to be run on a battery, you put a simple cache in it, and thus the cache performance is not going to be as good, right, as a more sophisticated cache, right? And you might say, well, what makes one cache better than the other? Well, it has to do with capacity, the size, there's some features they can put in there like victim buffers and prefetching and stuff like that. But in general, not all caches are the same. So you run your program, and the program might be slower than you expect, and that might be because you got a lot of misses, a lot more misses than you expected. Now, why do we care about misses? Because the ratio of hits and misses, or I should say the ratio of hits over all the memory accesses, right? So the percentage of memory accesses that are hits and the percentage that are misses is going to determine the average time it takes to access your memory. So I mentioned that small memories are fast, large memories are slow, but your actual access performance is going to be somewhere in between those two. It's going to be always going to be slower than your fastest memory, but it's always going to be faster than your slowest memory. So what determines where your access time fits between those two is determined by your hit rate, right? And the hit rate is determined by your program. So if you run a program like that Facebook Friends program I was telling you about, your hit rate's going to be really horrible because it just has a bad access pattern, because you have to load, you have to go to all my friends and then all their friends and all their friends, and you're going to be all over the place. Whereas on the other hand, if I'm doing a fast Fourier transform, I'm just trying to convert some signal from the time domain to the spectral domain, or if I want to multiply two matrices, well, the cache will be great then, because that's a very regular, structured, predictable type of access pattern. It depends on the application, right? And like I said, it depends on the memory system too. I can always upgrade my cache, make it bigger, and if I make my cache bigger, I might make my hit rate better too, right? Even for the same application. Okay, so that's, oh yes, a couple other terms here. So I mentioned hits, what a hit is and what a miss is. There's also hit rate and miss rate, which I also sort of implied. Hit rate is the percentage of accesses that are hits, and miss rate are the percentage that are misses. And then there's the hit time and the miss penalty. So the hit time is essentially what it costs if you get a hit. Now you might say, well, duh, that's just the access time of the memory, of the cache, right? Not necessarily. That's not necessarily true, because caches are more than just a regular memory. You might say, what do you mean? Memory is just a memory. It's just give me an address, and then you can load to that address or store to that address. You can read or you can write to that address, right? But a cache is a little bit more than that, because aside from being a memory, it also has to keep track of what addresses are in the cache, right? I mentioned that earlier, right? Think of a cache as a bag of addresses. And when I access an address, it's either in the bag or not. But how do you take a memory and then build functionality on top of that memory that allows it to keep track of a set of addresses that are in the cache? The cache has to keep track of what's in itself, basically, right? And that requires some extra logic. It requires some comparisons and some tags that we're going to talk about in a minute. And so that stuff contributes to the hit time. So the cache, even if you get a hit, can be slower to access than if you just were accessing that memory and you were restricted to just the size of that memory. Does that make sense? Okay, so keep that in mind. There's some trade-offs that you have to make. Like if you want to make the cache more sophisticated, you might think, well, great, my hit rate went down, I win. But you might not have won, because by doing that, you might have increased your hit time, right? So it's kind of a complicated trade-offs. The miss penalty is the time it takes to now this is a little bit, make sure this can be a little confusing. So when you get a miss, what happens? A miss requires that you go down to the lower level of the memory hierarchy and you retrieve the data that the block of data that you missed on, or the address that you missed on. Let me getting ahead of myself. The address that you missed on, right? But there's an added detail here. The cache has a fixed capacity. So anytime you get a miss, you bring in something from the lower level of the memory hierarchy, right, which is going to take time, But you also have to sacrifice something that's in the cache. You have to replace, because you can only fit so many words in your cache. So anytime you get a miss, it's not just that you have to wait for the data to come in from the lower level of the memory hierarchy. You have to sacrifice something that was already in your cache, and you better, that could be problematic, because sometime in the very near future the processor may want that thing that you're going to sacrifice, which will generate another miss when it didn't need to, because you had that thing in the cache. Make sense? So anyway, that's what goes into the miss penalty. Miss penalty includes accessing the slow memory and figuring out what to replace. Yes?
Does it also include the time it took to check if there was a hit?
Yes. Yeah, it includes that as well. That's right. Okay, so from the CPU's perspective then, what happens with a miss? What's the CPU, like how's the CPU deal with a miss? What's it do? Well, you guys, I think you talked about pipeline CPUs, right? And so you generally assume that the premise behind a pipeline CPU is that you divide up the execution of each instruction into steps. And you have to have those steps balanced. So you want to have, so you guys had fetch, decode, execute, memory, and write back. Those are the 5 basic steps of instruction execution. The reason that the authors of the textbook and the architects that designed these processors, the reason they chose those 5 sort of sub-steps, those 5 steps, is because ideally they all take about the same amount of time, right? So in other words, execute is add 2 numbers, memory is load or store, write back is write or register, right? The idea is that they all should take the same amount of time, because if they didn't, it wouldn't make sense to pipeline, right? The whole reason you're pipelining is because you're assuming that you're executing all 5 steps for 5 different instructions at the same time. That's where you get your instruction level parallelism, right? But if you get a miss in the memory stage of the pipeline, well, now you're in trouble, because I'm the memory stage of the pipeline. I get an instruction. The instruction says I'm a load. So I go out to the memory system and ask for the load. The memory system says, nope, miss. Step aside. So what do I do to the other instructions earlier in the pipeline that are about to crash into me? Well, basically, you got to stall them. So whenever you get a miss, the pipeline has to stall. At least the part of the pipeline that comes before the memory part. You can let whatever comes after, you can let that just flush out, right? But whatever comes before me, so in other words, the fetch, whichever instruction is being fetched, whichever instruction is being decoded, whichever instruction is being executed, they have to freeze. The instruction that's in the memory stage will basically say, oh, well, sorry guys, I have to wait for the miss to be serviced. And then what do I send into the write back stage every cycle during that time? Bubbles, no ops. So a stall is really 2 things. A stall means freeze part of the pipeline, and in the other part of the pipeline, insert the bubble, as my old Egyptian professor used to say, insert the bubble. Insert bubbles, basically put a bubble, because you can't allow a vacuum to develop. You have to keep putting bubbles in, which are no ops, basically useless wastes of work, just instructions that do nothing, that don't generate any results, right? So that's what's happening during that time. You're stalling. Make sense? So you guys talked about CPI, right? Cycles per instruction, right? So cycles per instruction for a pipeline processor, assuming there's never any stalls, is 1, right? I mean, once the pipeline is filled, you have to fill it. But once you get it filled, every cycle you're going to roll off a new instruction. But if you get a miss, then you stall. And so effectively, you're increasing the average number of cycles to execute every instruction, because you're ticking up the instruction counter, but you're not ticking off instructions, right? So you're burning cycles without ever finishing instructions. That is going to increase the cycles per instruction, right? So in effect, what I'm saying is that cache misses increase the memory access time, but once they increase it beyond one cycle, which is how much time you guys allocated towards the memory unit in your 5-stage pipeline, once they go beyond a cycle, which is essentially when you get a miss, those misses are adding to your CPI. So they're reducing your instruction throughput. They're slowing everything down, right? And so really, what's happening there is the memory is becoming the bottleneck for the performance. The CPU is essentially sitting there idle, not doing anything, waiting for the memory system to finish its miss penalty, right? Its miss time. And so that is what architects call the memory wall. And it turns out that most programs that you run that are high performance programs that take time. I don't know how many of you guys ever ran a program and had to wait for it to finish, because most programs that the average person use are sort of their performance is based on I/O, like how long it takes you to type something in, or how long it takes you to download a program from the internet, download data, or how long it takes to read from the disk, or something like that. But if you ever run like a scientific program or something that does number crunching, like a big data program, data analytics, even computer games to a certain extent with the graphical 3D rendering, that kind of stuff. Whenever you're sort of waiting for something and you wish the computer was faster, in most cases, the reason, the bottleneck, the thing that's preventing the computer from getting faster is the memory, is not the CPU speed, which means if you go to Best Buy, you buy a faster CPU, it doesn't do you any good. It's not any faster. Because CPUs get faster over time. They're slowing down now. They're sort of, the CPU performance is leveling off a bit. But historically, if I buy a CPU today and then I go to Best Buy a year from now and buy another CPU, it's going to be a faster CPU. But the memory is not going to be any faster. The RAM speed doesn't change very fast at all. In fact, there was a period of, they had this memory called DDR3 RAM. It basically didn't change speed for like 15 years. Now, just recently we got DDR4, and now they're coming out with high bandwidth memory. They're coming out with some new stuff now. But there was a long dry spell when every single CPU you bought basically had the same memory speed. It was 25.6 gigabytes per second of bandwidth. Latency was generally the same, about 25 cycles of latency, and that stayed the same for 15 years. So buying new CPUs just didn't make things faster. So that's why this chapter is important. Not only because memory is such a huge impact on computer speed, but because there's new memory technologies coming out. We need to be able to integrate them into the memory hierarchy. Okay, so let's move along. Okay, so let's revisit this idea of how is the cache physically organized? Because you guys probably know a memory, just a plain old memory, a RAM, a random access memory, is how long do I got? 215 to 210, right? 230. Thank you. Okay, so a regular memory is organized as a set of rows and columns, right? Memories are two-dimensional. So generally speaking, the row is the address, the memory address. You give it, that's a row ID, and the column is how wide the memory is. So it can be a byte or a word, right? That's just a plain RAM, right? Now, if you want to have a memory where you have a cache is really kind of, it's a little bit of an extra stuff. A cache is sort of like a hash table. Did you guys cover hash tables in data structures? So a cache is a little bit of extra stuff on top of a regular memory, because a cache has to not only have rows and columns and be sort of organized as a table like any RAM is, but it also has to have the ability to keep track of what's in it, right? It's got to have like a set. It's got to have a set of addresses. It's got to keep track of a set of addresses, right? So how does that work? Okay, so the simplest way to do that is you use a direct mapped cache, which means that you have your cache. In this case, you have a cache that's got 8 words in it. It's got 8, I shouldn't say words, I'm going to be more general. It's got 8 slots. 8 slots. Sometimes these are called cache lines, sometimes they're called cache blocks, but just think of these as slots. There's 8 possible bins that I can put stuff in the cache. And then you've got the memory space, the list of all memory addresses, right? Any arbitrary memory address, right? So for any arbitrary memory address, there's only one spot in the cache that could go, right? So basically what that means is that the cache, if it has 8 slots in it, you take all the memory addresses that are possible and you subdivide them into 8 groups. So every address belongs to a group. And if you give me any memory address, I can figure out what group it belongs in, and based on that, I know where the only place it could go in the cache. So it's direct mapped. It turns out that it's really trivial to implement that, because all you have to do is you have to do a modulo operation on the address. So you give me the memory address, and I do modulo by 8. Modulo is you divide and you take the remainder. That's the modulo, right? It's the remainder after division. You do the modulo, and that modulus is the slot number that address would go into, right? Now, because the caches are always divided into a number of blocks that are a power of 2, right? Like everything in computing is a power of 2. The way you think of this is the cache line, the cache block, the cache slot. The location in the cache is basically the low order bits, the least significant bits from the address. That forms the modulus. Does that make sense? So basically, what that means is if you look at the least significant bits of the address, you might say, how many bits? Well, in this case, 3, because there's 8 slots. So there's 3 bits I got to take out of the address, right? Because the log base 2 of 8 is 3. I take 3 bits out of the address, and that tells me exactly where that block would go in the cache, where that address would go in the cache. You guys with me? Okay. So now you might say, okay, well that's fine. I know where it goes, but how does the cache know? How does the cache keep track of what's in those 8 blocks? For that, it uses the tag. The tag is kind of like a fingerprint of an address, and it's really just the most significant bits of the address, right? So the rightmost bits of the address, the least significant bits, they tell you where the block goes in the cache, and then the most significant bits are the fingerprint, is what makes that address unique, right? And that's the tag. Okay, so what you have to do for a cache is the way that you organize the cache is you have slots for data. That's the data that's being held in the cache. But then you have a separate set of slots for the corresponding tag of each of the addresses that are in that slot, right? Then you might say, wait a second, that's like another whole memory you got to put in there. Yeah, it's like 2 tables. Think of it as 2 tables. I got 1 table for data and 1 table for tags. So then the cache, when the processor asks the cache to access an address, the cache has to figure out if the address is in the cache. So there's 2 steps. Step 1, I got to find which tag am I looking in, and that's just based on the modulus, right? Then step 2 is I have to compare the tag that's in the cache and compare that with the tag coming from the address coming from the processor. So now we've got 2 tags. You've got a tag that's potentially in the cache already, and you've got a tag that's being requested by the CPU. If they match, that's a hit. If they don't match, it's a miss, and whatever block was in that location, as determined by the modulus, you got to axe it and replace it. Make sense? So think of the cache as essentially data in tags, but there's one more thing. There's something called valid bits. Yeah, there's also a valid bit, which is kind of it's just kind of an overhead you have to add in there as well. The valid bit just determines whether there's anything in that line, right? So when you boot up your computer, every memory in your computer when you boot it up comes up as random data. It's just literally random bits. And so you have to be able to have this tag bits. There's 1 tag bit for every slot in the cache, and it's reset to 0, meaning that there's nothing in there, right? So it just, and then the first time you put something in that slot, you flip the valid bit to 1, and it stays like that until you power the machine off. Make sense? So a cache has 3 parts: valid bits, tags, and data. Okay, so here's some examples. These are pretty nice. So let's look at the cache. The cache is a table. Notice it's separated into 3 parts, 3 columns: valid, tag, and data. Notice there's 8 rows because there's 8 slots. I can put more. Yes.
So does the cache hold the data from memory or the memory address?
The tag is the address. The tag comes from the address, and the data is the contents of that address. Right? So the data. So this is something that is confusing. You have to think of every bit of data as having an address and data. So it's kind of like a website has a URL, and then there's the actual web page itself. So the tag is the address and the data. The data can change over time, obviously. As you store the data will evolve, right? But the tags are just the tags. The tags are the memory addresses. So the idea is that, and I'll show you an example here. I think it might be more clear as we go through the example. So for example, now there's a couple assumptions here. Let me back up here a second. One thing is there's 8 rows. Why is there 8? Well, there's 8 because I've sized. Remember, this is still a memory. So the more rows I have, the slower the slower it's going to be. And again, this is the thing I was telling you about at the beginning of class. Don't get caught up in technology. It's really about the size. So that's why we have level 1 cache, level 2 cache, level 3 cache, and now level 4 cache. The difference is how many of these rows are in each level of the cache. Every level of cache gets bigger. They're all based on SRAM. It's just size, right? The more rows you have, the longer hit time you have, the longer miss time you have, and all that other kind of stuff. So keep that in mind. But in this cache, we have eight slots. Now I'm also assuming that the data part is one word. What's a word? Word is whatever the word size of the computer is, 32 bits, 64 bits. If you have a 64-bit computer, it's 64 bits, right? Modern computers are 64. Even the ones in phones and tablets now are all 64 bits, right? So that's a word. Now you might say, why are you emphasizing word? What's the significance of a word? Memory addresses are byte addresses to this day, even though bytes are like pennies. Like no one cares about pennies. It costs 3 cents to make a penny. No one uses pennies. No one cares about pennies. But yet we still have pennies, and our whole monetary system is still based around the notion of the cent, a granularity of 1 penny, 1 cent. But yet no one cares anymore. But we cling to this. Same thing in computing. Everything's in bytes, bytes. But nothing fits in a byte anymore. Not even one word. Not even one character fits in a byte anymore. So we have this notion of a byte address and a word address, and this is a holdover from IBM back in the 60s. Decided we're gonna group data by 8 bits and call it a byte. So when I say word address, just think of that as memory address, but it's whatever it matches up to the size the one word stores in the data. Okay, so if my word address is 22, then I take this 22 and this is a conversion of 22 in decimal to binary. Okay? Make sense? So that's 16 plus 4 plus 2 is 22. Now, if I ask for this, the cache has to figure out where that goes in the cache. So I'm going to take the 3 least significant bits. That becomes my index. Now, the terminology gets a little weird. Index just means what slot in the cache does it map to. In a direct map cache, every row has 1 index value. So this particular address 22, because the modulo 22 modulo 8, or instead of doing modulo, I can just take the rightmost 3 bits. That becomes 110, which is 6, maps down here to row 6. Okay? Then I have to, once I know where that guy goes, where it maps in the direct map cache, then the cache has to say, well, is it already in the cache? I I don't know, it might be. Well, first thing you got to do is check the valid bit. The valid bit previous to this was a no, so it was not in the cache because the valid bit. But even if the valid bit were 1, I don't know why there's, okay, it should be 0 or 1. He's got no, yes or no, whatever. But anyway, originally, let me back up, sorry. Originally, the valid bit was 0, so we knew right from the valid bit that that thing wasn't in the cache. But even if the valid bit was set to 1, the next step would be to look at the tag. So the tag is whatever's left over after you back out the 3 least significant bits. So you take those bits out, and its tag is 2, right? So what we're doing is taking the word address, and we're decomposing it into a tag and an index, right? So the tag is 6, the index is 2, and once I have the tag and the index, I can figure out if that thing was in the cache, which of course it was not, so that was a miss, right? So after the miss is serviced, after the cache does what it needs to do in response to the miss, it will have brought in memory the word at that address from the low. It'll bring it up into the cache. Yes.
So it was a miss because is it valid?
The valid, in this example it was a miss because the valid was no. Yeah. But I was saying that even if the valid were 1, the next step would have been to compare the tag.
And if that was not the same tag, then it would also be.
Then it would be yes, that's right. The only way to get a hit is if the tag matches, the 2 tags match. So, there's 2 tags. There's a tag coming in from the request, and there's a tag that's in the cache. You're comparing those tags. So that's what the hit time is, by the way, is the hit time is the time it takes for the comparator to compare those 2 things.
Does it compare them by like subtraction?
It might, yeah, it depends how they design it. Usually comparators subtract, yeah. That's how I do it anyway. You could do an XOR gate too, where you do an XOR of all the bits and then fan all the results of that XOR into an OR gate, but I think subtract is more efficient hardware-wise. But not trivial. It still takes, there's still a logic propagation delay for that comparison. Okay, so here's another one, 26. 26 is 16 plus 8 plus 2, right? Yeah. So that's the binary version of 26. So take the least 3 significant bits that's row 2 or slot 2. Again, miss, tag is 1, 1, so I bring that once. So by the way, I didn't say this explicitly, but after the miss is fulfilled, I will have the data in the data, but the tag will have been updated as well, right? So misses change the tag, right? If I get a hit, I don't change the tag, but misses change the tag. Yes?
So the only time that like a miss or hit is only relying on the tag, never on the valid.
Never on the value, yeah, that's right. The value is only, the value, oh, the valid? I'm sorry, did you say the valid?
I guess I meant the value.
Valid.
That's the valid, right?
Valid, yeah. The valid is only for initialization purposes. So, yes, you're right. If the valid is the idea is that when you reboot your system, when you power it on, the tags will be randomized, and so there's a fear, there's a risk. The risk is the tag will match, but it was matched on a random number, like because you started up, so it might be a false. You don't want to get a false hit. So the valid bit is to prevent false hits on startup, basically. Now, what's the likelihood of that happening, really? Very low, right? But it could happen. So we want to guarantee that it'll never happen. So we use the valid to make sure that if that valid is no, then you're guaranteed to miss on that line.
Okay.
And then once you miss on it, then you'll flip the valid to true. There's actually other reasons too, actually. The other reason for that, by the way, is context switches. Say you're running 2 programs on your computer, right? Because you have a multitasking operating system, you can run multiple programs. When you context switch, when the operating system stops running one program and moves on and runs your other program, it has to invalidate the cache. And that's because the cache, these addresses are virtual addresses, and every program has its own virtual that's outside the scope of this course, but every program has a different memory space, and so we have to invalidate the cache when we context switch programs. It's not just on startup. But I'm getting into operating systems a little bit there. Okay, let's see. All right, so here's another one. So let's see. Yeah, so we had a miss. So this is not very clear, right? But what this is showing is this is an access pattern. So this is a series of 3 accesses, 3 addresses from top to bottom, ordered in time from top to bottom. And the first time we accessed word address 16, it was a miss. The second time we accessed it, it was a hit. Why? Because the first time it was a miss, we brought it into the cache. Then when we accessed it again, it was a hit, right? Right? Now you might say, of course, that's obvious, isn't it? Well, not necessarily, because if I missed on something in between these that was a different address, but it mapped to the same index 0, it would have thrown out this guy's address 16, right? So just because the reason I got a hit was not because I accessed the same address twice. It was because I accessed it twice and I didn't have any intervening accesses that axe that guy, right? That's called a conflict miss. If you cast out a cache line because it conflicted in the table, and then you later needed it and it was a miss, it's a conflict miss. So we've already covered, for some reason, he didn't want to cover these, but there's the 3 C's. There's compulsory, which means I have to miss the first time I get it. There's a conflict miss, which means if I miss because someone else claimed the cache line in the interim, right? And then there's a capacity miss, which is where I miss because I just didn't have enough cache lines to store the whole working set of my program, right? So those are the 3 causes of cache misses. This is a compulsory miss because it was the first time I accessed it. Yeah, there's a question?
I was just going to ask, so if it was 16, 8, 3, 16, they would all be misses.
Yeah, that's right. Yeah.
Okay.
Great example. Yeah, because 8, yeah, that's right, because 16 maps to index 0. Address 8 would also map to address 0, but with a different tag. And so that, yeah, that's exactly right. And that would have been a good example of a conflict miss. 8 and 16 both map to the same line, so they conflict with one another. I can't store them at the same time in my cache. Now, as you might imagine, there is a fix for that, by the way. They're called set associative caches. That's when you just have multiple copies of this. Real CPUs don't use direct map. They use set associative, meaning that instead of having only one available tag per index, you can have more than one. But then you need more comparators, because then you have to compare not one tag but multiple tags at the same time. And then if you get a miss even after that, then you have to decide which of the tags you want to replace. And that adds a whole new level of complexity, because you have to say, well, I want to replace the one I'm not likely to use again, so I have to keep track of which one is least recently used. But anyway, in a direct map, but you can still have conflict misses even with the set associative. Yes?
So with this direct mapping approach, is there really any way to control what is in your cache, or is it just purely based off the chance of what the last values are?
Yeah, there are techniques, like there's something called you can add a victim buffer. A victim buffer is a way, like if we take her example where you have 16, 8, 16, when you flush out 16 because it conflicts with 8, the index, you could have stored that 16, the first 16, in a victim buffer, which allows you to very quickly get it back. A victim buffer is essentially the last line that you threw out. Just keep it in a separate little place, just in case you need it again in the near future. If you,
Cache, kind of?
it's like yeah, but it's like only enough room for one of these things or two. It's smaller, but it's a place for victims to go where you don't completely kick them out, because there's a good chance that you'll need them. You know, that temporal locality will kick in, and you'll need them again, even though there was no place in the cache for them because of the direct mapping. Okay, that's another, extra feature that modern caches have.
Does it go in the victim buffer to memory then, like if another one came into the...
No, it stays in the victim buffer until it gets replaced in the victim buffer, in which case then it's gone.
Then it goes to back.
Well, that's a good question. So let me talk about that. That's a really good question. So So the last thing we want to talk to is about writing. So I think what you're getting at is when you throw out a line out of the cache, when you replace a line. By the way, when I say line, I'm just talking about one of those rows, slots. When you replace a cache line, what happens? Well, if you're only doing reads, if you're loading only, no problemo. Just throw it away. Just delete it. The problem is that when you first start talking about a cache, you usually think of everything in terms of read loads, right? But what happens if you store? What happens if I have a store instruction? Well, if I get a store, if I store to something, like if I store to this address, this line, I'm going to be updating the data in here, right? I mean, whether it was a store, forget about whether it was a hit or miss. At some point after I store, regardless of whether the thing was in there or not, I got to update the data in the cache. The question is, do you also update the lower level of the memory hierarchy? Or do you not do that and you allow the lower level of the memory hierarchy to then become stale? Meaning that if I write to this address, if I put new data in here, it'll be updated in the cache. Now you might say, well, no, you don't want to leave. What happens if you lose power or something? You won't, well, whatever, you lose power, you'll probably lose your DRAM too. But the point is that do you want to, what happens if you have multi-core processor? Let's put it that way. Let's say you have more than one processor. One processor may be hoarding updated data in its cache and not updating the lower level of the hierarchy. Right? In other words, another processor may go to the memory and get stale data, get out-of-date data, right? So what do we do about writes in the cache? Well, it turns out you got options. And this is something that not everyone has, there's no one's sort of, as far as I know, no one's kind of agreed on the best way to do this. Different CPUs do this different ways, even to this day. There's something called write back cache and write through cache. Write through cache is whenever I write to the cache, but then immediately write to the lower level of the memory hierarchy, right? Now, when I first heard that, I thought, well, that would be horrible because the whole reason we have a cache is to avoid accessing the bigger, slower memory, right? That's the whole point. So if you have a write-through memory, that would mean that every time you do a store instruction, whether you get a hit or a miss, you're going to pay the penalty of going to the big, slow memory, right? That sucks. I don't want to do that. Well, it turns out that it's not so bad because modern processors that use write-through, they use a write buffer. So the idea is that you write to the cache and then you write to the lower level of the memory hierarchy, but you don't make the CPU wait. You let it go because the CPU doesn't have to wait for the write to complete to the lower level of the cache. Why make it wait? Just say, look, I got it in the cache, you do your thing, I'll worry about writing this out to the memory. Now, on the other hand, if you run out of store buffers, then you're going to have to make the CPU wait. You have a finite amount of store buffers, right? But if you have a write-through cache, you don't necessarily have to make the CPU wait. Your question?
Is that why you can forward? Because you have like...
No, the forwarding happens internally. That's just inside the pipeline circuitry itself. And in terms of the memory system, if I do a store and it updates in the cache, and then I follow that up with a load to the same address, it'll get it right out of the cache. It'll just be a hit. So even though I might not have flushed it out to the main memory with the write through yet, doesn't matter because the CPU only sees the cache. And that's another good point. The CPU, the way the memory hierarchy works is that you can only see the memory that's immediately below you. You can't bypass it, right? So if I write to the cache and then I read from it, I'll get the updated value, even if it hasn't been updated to main memory. So that's a write through cache. The other way to do it would be a write back cache. A write back is when you allow the CPU to write to the cache without writing to the main memory. And you don't worry about updating the main memory until that cache line is replaced, right? If you do that, you have to add another bit here, another column called the dirty bit. The dirty bit denotes whether that cache slot has been updated relative to the memory below it, right? So that's write back. I don't think, I'm not sure. I don't think he's going to ask you. I'm not sure. He'll review this. So the write back cache factors into the performance of the cache, but I'm gonna let him cover that. I want to get back to what the performance is just in the general sense. So I mentioned this at the beginning of class: average memory access time. So this is the sort of problems that you'll have to answer for cache. There's a very important equation. The average memory access time is the hit time, which you always pay regardless. You know, whether you get a hit or miss, you're always going to pay for the hit time. That's the baseline access time of the cache. But then you have to add to that the miss rate times the miss penalty, right? So the miss rate, so generally speaking, this is kind of like a weighted average sort of. So if the hit time is 10 nanoseconds, and by the way, this might be in nanoseconds, or this might be in cycles, because you can express time in either one. So don't get confused by that. So whether I'm in cycles or seconds, you have the hit time, and then you multiply that by the miss rate times the miss penalty. So if the hit time is 10 nanoseconds, and the miss rate's 2%, and the miss penalty is 100 nanoseconds, then it's going to be 10 nanoseconds plus 2. 2% of 100, right? So it'll be 12 nanoseconds. That was what I was explaining at the beginning of class, where in the memory hierarchy, your access time on average is going to be slower than the fastest level of the cache, which is the hit time, right? It's going to be slower than that, but it's not going to be as slow as the bottom level of your memory hierarchy, which is you think of that as the miss penalty. You're somewhere in between. Where are you in between? Well, that depends on the miss rate. The miss rate will determine if you're closer to being as fast as the fastest memory, or you're closer to being as fast as the slowest memory. And the miss rate is a function of the locality, which is your program's behavior. What kind of program are you running? You'll run Facebook, it'll be very high miss rate, or you'll run matrix multiply, and it'll have a very low miss rate, right? So that's the you definitely want to memorize that. And then finally, I think the last thing, I got a couple minutes. Let's see, there's a couple other things here. Okay, so the last thing I want to mention is, this is something that used to always confuse me. So you've got average memory access time, right? I understand that. It's the average amount of time it takes to access the memory. But then you've got, going back to chapter 2, right, or chapter 1, at the beginning of the class, you guys should have been talking about CPU time, right? So CPU time is the number of instructions, right, times the CPI times the cycle time, right? Right. So if I want the computer to be faster, I can speed up the clock, or I can lessen the number of instructions, or I can decrease the number of cycles it takes to do it, the cost of each instruction, the cycles per instruction, right? How does the memory system relate back to this? This is the part that gets a little weird. If you notice, the CPI has now been split into two parts: the CPI of the execution and the CPI of the memory system. So when you calculate the CPU time, see, average memory access time doesn't directly tell me anything, because I don't know how often my program is accessing memory, right? Like if I have a program, I can calculate the average memory access time, but if that's a memory intensive program, that program's runtime will be affected to a greater degree by the average memory access time than a program that doesn't access memory as often, right? So how do I tie everything together? Well, I have to calculate the number of memory stall cycles per instruction on average, right? And I have to incorporate this into CPI. So what this is saying is, when you execute an instruction, you can have stalls from two different sources. You can have a stall because of a forwarding, a data hazard, right? Data hazards, control hazards, branches, that kind of stuff. So you can have stalls from the internals, right? Or you can have a stall from the memory system, because you get a cache miss. There's two kinds of stalls now. So you're going to have to factor both of those kinds of stalls in when you're calculating the CPI, right? You may have a super awesome computer that never stalls because of the instructions, but if the memory is really slow, then your CPI will skyrocket because of the memory system, right? So you have to factor both of those things in, okay? All right, great. Thank you, guys.